All right, today is our third video on linear regressions, and we're going to be looking at pages 9 through 12, and we are going to be talking about residual effect. All right, so you may have used a shape of data in a scatter plot or the correlation coefficient to help you determine whether a linear model is an appropriate model for the data set. For some data sets, these measures may not provide enough information to determine if a linear model is most appropriate. In order to be a safe driver, there are a lot of things to consider. For example, you have to leave enough distance between you and the car in front of you in case you need to stop suddenly. The table shows the braking distance for a particular car when traveling at different speeds. All right, so this is going to be our first example of using residual effect. So the first thing we're going to do is construct a scattered plot and then calculate the line of best fit. So we're going to graph it on our paper first. Let me make my pen a little bit smaller. Maybe smaller than that. All right, so I'm just counting by tens on the bottom. And I'm counting by 40s on my y-axis. So 40, 80, 120, 160, 200, 240, 280, 320, 360, 400. All right, and then I'm just going to plot my points from there. So 30 and 48, 40, 80, 50, 120, 60, 180, 70, 240, and 80, 320. All right, so that's what your graph should look like. And then by now you should feel comfortable enough typing these tables into Desmos to get the equation. So I'm just going to give you the equations today because we do have 4 pages to go over, so to save us a little bit of time. So when you type this stuff into Desmos, you should get y equals 5.4x minus 134. And then our correlation coefficient was 0.99, which is strong and positive correlation. All right, number 3, we're going to write a function to represent the braking distance given the speed of the car. Interpret the function in terms of this problem situation. So all that means is we're going to take our line of best fit and we're just going to write it in function form. So d of s equals 5.4s minus 134. All right, and then to interpret it, for every 1 mile per hour in speed, braking distance increases 5.4 feet. All right, so in addition to the shape of the scatter plot, the correlation coefficient, and the correlation coefficient, one additional method to determine whether a linear model is appropriate for the data is to analyze the residuals. A residual is a vertical distance between an observed data value and its predicted data value using the regression equation. All right, so number 1, we're going to complete the table. All right, so they already have the speed and the observed distance. So we have to find the predicted braking distance. All right, so how we're going to do that is we're going to plug in these x values into our equation. And whatever we get, that's what's going to give us our predicted value. All right, so when I plug 30 in my calculator, so I'm going to do 5.4 parentheses 30 minus 134. Okay, when I type that in, I get 28. All right, then I do the next one. 5.4 times 40 minus 134. And that's going to give me 82. Then I'm going to do 5.4 times 50 minus 134. And that's going to give me 136. All right, then you keep doing that for each one. So for 60, I get 190. For 70, I get 244. And for 80, I get 298. All right, so that's how we get the predicted braking distance. Now we have to find the residual value, which is observed minus predicted. So observed minus predicted. So for the first one, I'm going to do 48 minus 28, which gives me 20. Then I'm going to do 80 minus 82, which gives me negative 2. 120 minus 136 is negative 16. 180 minus 190 is negative 10. 240 minus 244 is negative 4. And 320 minus 298 is 22. All right, and that's how you find the residual value. All right, so let's flip over to the next page. So we want to examine the scatter plot and the residuals. So A says, show the residual value on the scatter plot by connecting each observed value to its predicted value using a vertical line segment. All right, so for the first point, our observed value was 48, but the predicted value was 28. So 28 would be like right here. All right, our predicted value was, our observed value was 80, and our predicted is 82. And I'm just going to connect them. So on the graph, it shows our observed was 120, but our predicted is 136. The next one, our observed was 180, but our predicted was 190. Our observed was 240, but it was actually 244. And then 320 was our observed, but the predicted was 298. All right, so when does a residual have a positive value? All right, and that's when observed is greater than predicted. And the residual has a negative value when predicted. I don't even know if that's how you spell predicted. It's not. There's no I there. All right, so it's bigger when observed is greater than predicted, and it's less than when predicted is greater than observed. All right, so the residual data can now be used to create a residual plot. A residual plot is a scattered plot of independent variable on the x-axis and the residuals on the y-axis. Construct a residual plot of the speed and braking distance. All right, so looking at this. All right, so when we were going 30 miles an hour, our residual was a positive 20. When we were going 40 miles an hour, it was negative 2. When we were going 50 miles an hour, it was negative 16. Oh, wait, that's 50. I need to go over. When it was going 60 miles an hour, that was negative 10. When it was going 70 miles an hour, that's negative 4. And when it was going 80 miles an hour, that was 22. So that's our residual plot. All right, so now we're going to interpret each residual in the context of the problem. All right, so remember, if it's positive, it's greater. If it's negative, it's less. So 30 miles per hour is 20 feet greater because it's in that positive section. 40 miles an hour is 2 feet less. 50 miles an hour, 16 feet greater. No, 16 feet less. Then 10 feet less. 4 feet less. And then 22 feet greater. These are our residual values. Okay, and then if it's in the positive region of our residual graph, so up here, it's greater. If it's in our negative region, it's less. All right, number 5, what pattern, if any, do you notice in the residuals? So it started out greater. Then less, then it went to greater again. All right, next page. So the shape of a residual plot can be useful to determine whether there may be a more appropriate model other than a linear model. Okay, so these are some examples for you to look at. And now we're going to go over one last example. So over the last semester, Mr. Finch kept track of a number of students' absences. Now that the semester is over, he wants to see if there's a linear relationship between the number of absences and a student's grade for the semester. The data he collected is in the table. So first we have to graph it. So this is our x values, this is our y values. So 0 is 95, 5 is 73, 3 is 84, 1 is 92, 2 is 92, 3 is 80, 10 is 65, 0 is 90, 6 is 70, 1 is 88. All right, so our x value is the number of absences, and y is the grade that they'll have. All right, so describe the association shown in the scatter plot. So our graph is going down. Okay, so that tells us it has a negative linear correlation. All right, and then we're going to determine the linear regression line. So remember I said y'all should feel comfortable finding this in Desmos yourself, so I'm going to give it to you today. But if you don't, feel free to pause the video, go through on Desmos, and then check your work with what I have. So our equation is y equals negative 3.1x plus 92.6. And every absent day, a student's grade drops 3.1%. And then our R value was negative 0.94. All right, so you can find all of that in Desmos if you type it in. Now we're going to fill out this big residual table on the back. So first we're going to find our predicted value, okay? So that's when we're plugging it into our equation. So our equation was y equals negative 3.1x plus 92.6. All right, so I'm taking these numbers and plugging them in for x. So I would have negative 3.1 parentheses 5 plus 92.6. And that would give me 77.1. Then I would go to the next one. Negative 3.5 times 3 plus 92.6 is 83.3. So I'm going to look for all of my 3's, and those will all have 83.3. All right, then I'm going to plug a 1 in, and that's going to give me 89.5. So all of my ones should have 89.5. The next one is 2, and that gives me 86.4. I don't see any other 2s. Next I do 10. Which is 61.6. All right, 0, they found it for us, so 92.6. And then I need to plug a 6 in, which will give me 74. All right, now that I have all of my predicted values, I need to find my residual. So that's when we take our observed and subtract the predicted. So I'm just subtracting these numbers together. Okay, so I get negative 4.1, 0.7, 2.5, 5.6, negative 3.3, 3.4, negative 2.6, negative 4, and negative 1.5. Now we're going to do the interpretation. So they give us an example. So for 0 absences, the actual grade is 2.4% greater than the predicted. Okay, so on your chart, I just want you to put this part, if it's or the percentage greater or percentage less. Okay, so remember, if it's negative, it's less. If it's positive, it's greater. So this is 4.1% less. Okay, that one's positive, so 0.7% greater. 2.5% greater. Okay, and that's all you have to do for the interpretation, because that's a very tiny space for a very long sentence, so I didn't want y'all to have to write all of that. And then the last thing we're going to do is construct the residual plot. All right, so for 0 absences, we had a positive 2.4. And we had a negative 2.6. No, that's not right. All right, for 5, we only had 1, and it was negative 4.1. For 3, we had positive 0.7. And we had a negative 3.3. For 2, we had 5.6. For 10, we had 3.4. For 6, we had a negative 4. And then for 1, we had 2.5. And negative 1.5. And so that's what your residual plot would look like. So that ends the notes on residual effects.